All right, so get this. We're going deep on CDMA today.
CDMA, huh?
Yeah, like how your phone talks to those cell towers.
Right.
But ever wonder how all those conversations don't totally jam each other up?
Yeah.
That's where CDMA comes in. And we've got all sorts of goodies to unpack. Lectures, tech papers, even some Q&A comparing it to, other ways phones connect.
Sounds like fun.
Yeah, should be interesting. So to kick things off, any thoughts on CDMA?
Well, it's kind of like, imagine a party, right? Everyone's whispering secrets,
Yeah.
but you can still hear your friend perfectly.
Sneaky.
Right.
But CDMA, that's, what is it, code division multiple access?
Yeah, you got it.
Doesn't exactly scream party whispers to me.
Well, it's the code part that's key here.
Like a...
See, in older tech, like FDMA, which kind of slices up the bandwidth, gives each user a little piece.
Like a pie chart.
Yeah, exactly. But CDMA lets everyone use the whole frequency range all at once.
Whoa.
Yeah, the trick is it gives each conversation its own, secret scrambling code.
So it's less like dividing a pie and more like everyone's talking in different languages.
Exactly. Only the intended listener can understand.
That's pretty cool. So it's called spread spectrum, right?
You know it. Your data gets mixed with a special code, kind of spread across a wider bandwidth.
Wider bandwidth.
Yeah, and at the other end, the same code unscrambles it, filters out all the other chatter.
So my phone's like a secret agent decoding messages.
In a way, yeah.
Okay, I'm with you so far. But if everyone's on the same frequency, how do those signals not, trip over each other?
Well, that's where those orthogonal codes come in. Remember those from the material?
Oh, yeah, right. Orthogonal codes.
They're like, imagine puzzle pieces designed to fit together perfectly.
There's no overlap.
Exactly. Mathematically speaking, their dot product, it's a way to measure how much two things point in the same direction. It's zero.
So they don't interfere.
Minimal interference.
Yeah.
So even in a crowded space, your phone can pick out its message.
Makes sense. That's really slick.
It is. It's pretty cool.
So to make sure I've got this, thanks to these orthogonal codes, my phone can have a clear conversation, even when it's surrounded by all this wireless chatter.
You got it. That's CDMA in a nutshell.
Okay, that's pretty impressive. But, to really get this, maybe we should try a real example.
Yeah, let's do it.
All right, so in that CDMA codes PDF, there's this example.
Right.
Let's say a user has the code 1-111.
Okay, good one.
They want to send a 1. So their signal, it gets spread using that code, right?
Yeah, that's the first step.
But send to 0, they got to flip the script.
Exactly. They multiply each part of the code by -1, basically reversing the pattern.
So the code's like a stencil, shaping the signal before it goes out.
Yeah, I like that analogy.
Okay, so far so good. But then how does it know which code to use to unscramble all this jumbled mess coming in?
Ah, good question.
It's not like my phone has a list of everyone's secret codes, right?
Well, it actually does, kinda. It has a copy of each user's code. Think of it like a set of keys. It tries each one to see which unlocks the message.
Oh, clever.
It multiplies the incoming signal, the combined one, with each user's code. And if the result, when you add it all up, if it's positive, it knows a 1 was sent.
And if it's negative...
then it's a 0.
Wow, that's like solving a tiny puzzle for every bit of data.
It is. It's pretty amazing.
It is. But hold on, what happens when signal strengths are all over the place?
What do you mean?
What if someone's right next to the cell tower and I'm miles away? Wouldn't their signal just drown mine out?
Yeah, that's the near-far problem.
The near-far problem.
Yeah, it's one of the big challenges for CDMA. It's like, you're at a concert, right?
Yeah.
Someone's blasting your eardrums, standing right by the speaker, makes it hard to hear someone shouting from across the field,
Yeah, I get it.
CDMA uses power control to deal with this.
Power control.
Yeah, the cell tower is a sound engineer telling the loud ones to turn it down and the quiet ones to speak up.
That's a cool way to think about it.
Right. But it's tricky to manage, in real time.
Yeah, I can imagine. So CDMA, it sounds powerful, but pretty complicated too.
It is. There's a lot going on under the hood.
So what makes it worth all the hassle? What are the upsides?
Well, one of the biggest ones is its resistance to interference.
Interference.
Yeah, because the signal's spread out. Narrow band noise doesn't really mess with it that much. Trying to disrupt a conversation by playing one loud note, it just wouldn't be very effective.
So CDMA is kind of tough. It can handle those noisy environments.
Yeah, exactly.
Yeah.
Especially in, crowded cities, it's a big advantage.
That makes a lot of sense.
Yeah.
So what else? What other perks does CDMA have?
Well, there's soft handoff.
Soft handoff.
Yeah, with older tech, your phone had to completely disconnect from one tower before grabbing onto the next,
Right.
which could lead to, drop calls. CDMA, though, it lets your phone connect to multiple towers at the same time during that transition.
Oh, so it's like, I don't know, two trapeze artists holding on during a midair switch.
Yeah, exactly. Less chance of things going wrong.
That's a great feature. Especially for, well, someone like me. Always on the go.
Yeah, it makes a big difference.
Okay, but every rose has its thorn, right?
Yeah.
What are the downsides of CDMA?
Well, as we said, the complexity of power control and code allocation, that's a big one.
Yeah, definitely sounds tricky.
And because it relies on all these intricate codes, CDMA systems, they're just generally more complex to design and maintain.
More complex. Okay.
Yeah.
So it's a trade-off then.
It is, kind of.
More complexity for better performance.
Exactly.
Huh. Makes you appreciate all the engineering that goes into something we use so, effortlessly.
It really does. It's amazing.
It is. So to get the bigger picture here, where does CDMA fit in the history of mobile networks?
Oh, good question.
Remember those clunky 3G phones we all had back in the day?
Oh, yeah, I remember those.
CDMA was a big deal back then, right?
It was. Offering faster data speeds, enabling things like video calls, all that.
Those were the days.
Right.
But now it's all 4G and 5G, so what happened to CDMA?
Well, it kind of laid the groundwork for those advancements, but it's less prominent in the newer network.
Less prominent. Okay.
Yeah, 4G mostly uses LTE. That's a different tech altogether.
Right.
And 5G is even more advanced. But CDMA is still around, powering things like, satellite communications, some military applications.
So it's kind of a hidden hero now.
Yeah, working behind the scenes.
Okay, that makes sense.
Yeah.
So we've talked about how CDMA lets all these users share the same frequency.
Right.
But what happens when your phone, moves between different networks, like different areas?
That's where mobile IP takes center stage.
Mobile IP.
Yeah, it's all about making sure your connection stays smooth, even when your location and your IP address are constantly changing.
Constantly changing, okay.
Yeah.
This is getting really interesting. I'm starting to see all the pieces that make mobile internet work.
It's a lot more complex than people think.
It is. So let's dive into mobile IP next.
They're good to me. Let's do it. So picture this. You're watching, I don't know, your favorite show on your phone.
Okay.
And you're walking, right, from your home Wi-Fi to, say, a coffee shop's network.
Right.
And the video just keeps playing, no hiccups, nothing.
Yeah, the magic of the internet, right?
I don't wonder how that's even possible.
Honestly, yeah, it's one of those things you don't think about until it stops working, right?
Exactly. But that's where mobile IP swoops in to save the day.
Mobile IP, yeah.
Yeah, it's all about handling those network changes, making
Yeah.
sure you stay connected.
So it's like, what, a network juggler?
Kinda, yeah. Think of it this way. You have your home address, right?
Sure.
But when you're traveling, you might use a temporary one, so your mail still gets to you.
A forwarding address.
Exactly. Mobile IP does the same thing for your device.
Okay, so what's my phone's home address in this scenario?
It's permanent IP address, within its home network.
Right, the home Wi-Fi.
Yep. And when you roam to a new network, you get a temporary care of address, or COA.
COA.
And mobile IP makes sure all your internet traffic, it gets routed properly no matter where you are.
So, who's in charge of this whole forwarding service?
Well, remember that mobile IP PDF,
Okay.
it mentions a home agent and a foreign agent.
Oh, yeah, right, those guys.
They're the key players here.
So what do they actually do?
Well, the home agent, think of it like a dedicated mailroom in your home network.
Okay.
It keeps track of your permanent address, and it knows your current COA.
So it's like the control center.
Exactly. And the foreign agent, that's like the local post office in the network you're visiting.
So like the coffee shop's Wi-Fi.
Yeah, it gives you temporary COA, helps forward those packets to you.
Okay, so let's break this down, step by step. Say I'm walking into that coffee shop, connecting to their Wi-Fi. How does my phone know where to send, its internet requests?
So when you connect to the coffee shop's Wi-Fi,
Right.
your phone, it discovers a foreign agent, and it registers its COA.
Registers the COA.
Yeah, and then the foreign agent, it tells your home agent, hey, this device is hanging out with me now.
So both agents are in the loop about my phone's location.
Exactly. They got to stay in sync.
Okay, got it. But then what happens when I try to load a website? Does my phone just send the request straight to the server?
Well, not quite. This is where it gets interesting.
Okay.
The website server, it sends the data to your home address, like you're still on your home Wi-Fi.
Like I never left.
Right. But that's where the home agent steps in.
What does it do?
It intercepts those packets and it encapsulates them.
Encapsulate?
Yeah, basically puts them inside another packet addressed to your temporary CoA.
So it's like putting a letter inside another envelope with the right forwarding address.
You got it. Pretty clever, huh?
It is. It is. So then what? This special package, it gets shipped to the coffee shop Wi-Fi.
Yep. That's called tunneling.
Tunneling.
The home agent, it creates a tunnel to your CoA at the coffee shop.
Like a secret underground passage.
Exactly. The foreign agent, it receives the tunneled packet, takes it out of its little package, and delivers the original data to your phone.
So from my perspective, it's like business as usual.
Exactly. Seamless.
But behind the scenes, there's all this tunneling and forwarding going on.
It's a whole hidden world, making sure you stay connected.
The magic of mobile internet.
It is. It's pretty amazing.
It is. But hold on. Our source also mentions different types of CoAs.
Right.
Can you break this down for us?
Sure. There are two main types.
Okay.
Foreign agent CoA and co-located CoA.
Whoa. Okay. Those are mouthfuls.
Yeah, I know, right? So foreign agent CoA, that's basically an IP address of the foreign agent itself.
So it's like everyone at the coffee shop sharing the same post office box.
Exactly. If you're sitting next to someone, your phones might have the same CoA.
Interesting.
Co-located CoA, though, that's a separate IP address that your device gets directly from the foreign network.
So it's like getting a temporary apartment number while you're away from home.
Exactly. And it often uses DHCP to do that.
DHCP, right? That's Dynamic Host Configuration Protocol.
You know it. So yeah, you could have two IP addresses, your permanent one, and a temporary one from the coffee shop.
That makes sense. So how do you choose between these CoA types?
It depends on how the network's set up. And the security needs, it can get pretty technical.
Yeah, I bet. Okay, so this is all making sense, but doesn't all this tunneling and forwarding add extra delays?
It can, yeah.
Especially for things like, I don't know, video calls or gaming, where every millisecond counts.
Right, good point.
Does mobile IP slow things down?
Well, it can add some latency, that's true.
Latency.
Yeah, but mobile IP has gotten smarter over time. There are optimizations to help with that. Yeah, like once a connection is established, it can allow direct communication between your device and the server, bypassing the home agent.
So it's like realizing, hey, I can just mail things directly to your temporary address. No need to route everything through your home.
Exactly. Cuts down on those delays.
Smart. Any other cool optimizations we should know about?
Well, there are fast handoffs.
Yeah.
Those are designed to minimize disruption when you're switching between networks.
Fast handoffs, okay.
Yeah, the goal is to make it so quick you barely notice the transition.
That's impressive.
And there are binding updates. That's where the foreign agent, it proactively tells other network nodes about your new location so they know where to send data.
So it's like spreading the word, letting everyone know where to find you.
Exactly. Keeps things running smoothly.
Okay, so mobile IP, it's not just about basic forwarding. It's got all these tricks up its sleeve.
Yeah, it's a whole system working together to make sure you stay connected.
All right, I'm following you so far. But we're not done with the whole mobile communication puzzle yet, are we? Now we got to talk about mobile TCP.
You're right, we do.
So mobile IP, it gets those packets to our devices, even when they're moving around.
Right.
But ensuring that data actually gets delivered, reliably over those sometimes finicky wireless networks.
Yeah.
That's where mobile TCP comes in.
Exactly. Different job, same goal.
Yeah.
Keeping you connected.
Okay, so I remember TCP, that's Transmission Control Protocol. It's
Yeah.
like the internet's delivery guarantee, making sure data arrives in order, no errors, all that.
You got it. But why do we need a special version for mobile devices? Can't regular TCP handle it?
Yeah, that's what I'm wondering.
Well, wireless networks, they're just inherently less reliable than wired connections.
Less reliable, okay.
Yeah. Signal strength can fluctuate. Interference pops up. Those handoffs we talked about, they can lead to dropped packets.
Right.
Regular TCP, it can misinterpret these issues as network congestion and slow things down unnecessarily.
So it's like freaking out, thinking there's a traffic jam when it's really just a few potholes in the road.
That's a great way to put it. So yeah, that's why we need mobile TCP.
Mobile TCP.
It's designed to tell the difference between wireless hiccups and real congestion, optimizing for those less than perfect connections.
Makes sense.
Yeah.
So how do we make TCP more mobile friendly then?
Well, our source mentions something called indirect TCP or ITCP.
Indirect PCP.
Yeah, basically we split the TCP connection into two segments.
2 segments.
One runs between your phone and the foreign agent. That's usually pretty stable.
Okay.
Regular TCP works fine there. But the other segment, the one between the foreign agent and the server, That's where the mobile-specific magic happens.
So it's like having a middleman who's really good at dealing with those unpredictable wireless links.
Exactly. ITCP shields regular TCP from all the chaos.
Shields it from the chaos. Okay.
One benefit is it reduces latency during handoffs because the connection between your device and the foreign agent, it doesn't need to reset every time you move.
Right, because that local connection, it's less affected by the bigger network changes.
Exactly. Smart.
It is. Are there any other advantages to ITCP?
Well, it's also very transparent.
Transparent.
Yeah, apps don't need to be modified to work with it, so it's a behind-the-scenes improvement.
Always a plus.
Yeah.
But I'm guessing there are some downsides too, right? What are the trade-offs?
Well, the main one is it needs changes to the network infrastructure.
Infrastructure.
Yeah, foreign agents got to be set up to handle this TCP segmentation,
Right.
which can be complex and expensive, to be honest.
So it's not a quick fix.
Not really. And there are also some security concerns, if the foreign agent isn't trustworthy.
Ah, right. Because it has access to all the data.
Exactly.
So ITCP, it's not a one-size-fits-all solution.
Nope. Are there any other ways to make TCP more mobile-friendly, though, that don't need all those infrastructure changes?
That's what I was going to ask.
Well, there's snooping TCP.
Snooping TCP, okay.
It's a bit sneakier. It doesn't require actually changing the TCP protocol itself.
Sneaking around the rules.
Kinda. The foreign agent, it acts like a silent observer.
A silent observer.
Yeah, caching packets, doing local retransmissions if it detects any loss.
So it's like a helpful ghost in the machine, fixing errors before they cause problems.
Yeah, I like that. And since the server, on the other end, it's totally unaware of what's happening,
Right.
snooping TCP is totally transparent to the user and the apps.
Best of both worlds, then.
Kinda, yeah. Better reliability without those complex changes.
I like it. Any other mobile TCP tricks worth mentioning?
Our source mentions link layer mechanisms. Those work at a lower level, closer to the actual wireless signal.
Lower level.
Yeah, think of it like error correction built into the language of the radio waves themselves.
Whoa, that's getting pretty deep.
It is, and there are delayed acknowledgments. Those reduce the back-and-forth chatter needed for reliable transmission, especially over high-latency connections.
Less chatter, faster data.
Right. It's all about optimization.
Yeah, it seems like there's this constant tension between reliability, speed, and efficiency.
There is. Finding that sweet spot, it's a real challenge.
It must be. Well, we've covered a lot of ground today.
We have.
CDMA, mobile IP, and now mobile TCP. My brain's starting to feel like a cell tower processing all these signals.
I feel ya.
It's amazing to see how all these pieces fit together, though.
It really is. It's a testament to human ingenuity, honestly.
It is. And as we move towards, faster and more complex networks, with 5G and beyond, all these underlying principles, they're just going to keep evolving.
Absolutely. But the core ideas, sharing resources, ensuring reliability, connecting people, those will always be central.
They will, yeah.
It's fascinating, really.
It is. But before we get ahead of ourselves, let's recap what we've learned about mobile IP and mobile TCP.
Good idea.
So we started with mobile IP, understanding how it keeps our devices connected, even when they're hopping between networks.
Right. Constantly on the move.
And those home agents and foreign agents, they're working together to forward our data, using tunneling to create a seamless path.
Like a secret network of tunnels.
Exactly. And we learned about all those optimizations, route optimization, fast handoffs, binding updates.
Lots of clever tricks to keep things running smoothly.
Yeah, it's impressive. And then we talked about mobile TCP, understanding why regular TCP kind of struggles with those unpredictable wireless connections.
Right. It's not built for that.
And we saw how techniques like ITCP and snooping TCP, they can boost reliability without sacrificing transparency.
Silently making things better.
Exactly. And we even touched on those lower-level tricks like link layer mechanisms and delayed acknowledgments, all those multi-layered approaches to making mobile communication better.
It's all connected, literally.
It is.
Yeah.
But our mobile devices, they're more than just, portals to the internet.
Sure.
They can also talk directly to the network using special codes.
Oh, yeah.
And that brings us to our next topic, USSD.
USSD, those star hash codes.
Yeah, the ones I use all the time but never really understood.
Let's decode those secrets next.
Okay, so USSD.
USSD, yeah.
I'm always using those star hash codes, but I've never really gotten what's going on behind the scenes.
Well, it stands for Unstructured Supplementary Service Data.
Unstructured Supplementary Service Data.
Catchy, right.
It really rolls off the tongue.
But basically, it's how your phone has a quick chat with the network using those short codes.
A quick chat, okay.
Yeah, it's part of what's called the Man-Machine Interface, or MMI.
MMI.
It's all about how we interact with devices,
Right, right. So like when I dial #06 tag to see my phone's IMEI number,
Yep.
that's USSD doing its thing.
Exactly. It's like a secret language for uh, accessing hidden features, network services.
Hidden features, okay.
And the cool thing is, it doesn't need a fancy smartphone or even a data connection.
That makes sense. I remember using USSD codes on those old Nokia phones way back when
Oh yeah, those are the days.
they were. So what else do we use USSD codes for?
Well, think about checking your prepaid balance, activating a data package, even using mobile banking, stuff like that.
Okay.
A lot of telecom operators, they rely on USSD for these kinds of interactions.
Right, makes sense. Our source material, it actually has examples from like Dialog Axiata and Mobitel.
Oh yeah, those are good ones.
With Dialog, you can dial #678 tag, and it brings up this whole menu for all sorts of services.
It's like a little text-based app right on your phone.
Exactly. But I'm noticing a difference here between like device USSD codes and network USSD codes.
Oh, good observation.
What's the difference?
So device USSD codes, like the one for checking your IMEI,
Right.
those are built into your phone. They don't need a network connection.
Okay.
But network USSD codes, those are talking directly to your telecom operator system.
So it's like the difference between using your phone's calculator app and calling your bank's automated phone system.
Haha, yeah, that's a great way to put it. And just like those automated systems, network USSD codes, they can be specific to each operator.
So a code that works on Mobitel might not work on Dialog.
Exactly. Each operator has its own set of codes and menus. Like Mobitel uses #888 tag for their self-care portal,
Right.
while Dialog uses #67H tag for something similar.
Okay, I'm seeing the potential here. USSD, it's simple. It works on almost any phone.
Accessible, yeah.
What other interesting things can we do with USSD beyond those basic telecom things?
Well, it's become really important in areas with limited internet access.
It's limited internet access.
Yeah, our MMI PDF talks about how it's used for mobile banking.
Mobile banking, okay.
People can check their balances, transfer money, even pay bills, all using USSD on a simple feature phone.
Wow, so it's like bringing financial services to people who might not have, like, easy access to a bank?
Exactly. It's really powerful.
It is. And it's not just banking, right?
Nope. USSD is being used in healthcare, agriculture, education, all sorts of fields.
Wow.
Healthcare workers can report disease outbreaks, track patient data, even in remote areas. Farmers can get weather updates, check market prices.
That's amazing.
Students can take quizzes, access educational content. The possibilities are huge.
It really is incredible how this, like, seemingly basic tech can have such a big impact.
Especially in those places where internet access is limited.
It's making a real difference.
Mm-hmm.
But I'm guessing USSD has its limitations too.
Well, of course. One challenge is the short timeout period.
Short timeout.
Yeah, USSD sessions, they tend to expire pretty quickly.
Oh yeah, I've been there. Just when I'm about to find what I need, the session time's out, and I have to start all over.
It's like a race against the clock.
It is. What else? What other downsides are there?
Well, there's the memorization factor, you know. You got to remember all those specific codes.
Right. And there's so many of them.
Exactly. It would be great if there was like a universal directory or an easier way to search for them.
Yeah, I agree. What about multimedia? Can you send, like, pictures or videos with USSD?
Unfortunately not. It's mostly limited to text.
Text only. Okay.
It's great for those quick interactions, simple services, but not ideal for anything too complex or data heavy.
Right, right. So it's a powerful tool, but it definitely has its niche.
Definitely.
Well, we've covered a lot of ground today. CDMA, mobile IP, mobile TCP, and now USSD. It's like we've gone from the basement to the attic of the mobile communication house.
We've taken the grand tour. It's amazing how all these technologies work together to keep us connected, isn't it?
It is. And it all comes down to this, like, intricate dance of signals, codes, protocols, this hidden world that most of us never even think about.
It's a testament to human ingenuity, really.
It is. And as we move towards, even faster and more complex networks with 5G and beyond, all these underlying principles, they'll keep evolving.
Oh, absolutely. But the core ideas, sharing resources, ensuring reliability, connecting people, those will always be at the heart of it all.
We will, yeah. I'm walking away from this deep dive with a whole new appreciation for what's happening inside my phone. I'm going to look at those star hash codes in a whole new light now.
That's the beauty of knowledge, isn't it? It changes how we see the world, even the everyday things we take for granted.
It really does. So to our listeners, we'll leave you with a final thought. If you were designing the ultimate mobile network, what would be your top priorities? Speed, reliability, security, accessibility. What features from all these technologies we've discussed would you combine to create the perfect connected experience?
Keep those ideas flowing because you never know what might spark the next revolution in mobile communication. Until next time, keep exploring and stay curious.